Hello dear students. In this last video for nonlinear programming, we review some other concepts of nonlinear programming, the other methodologies to solve some types of problems, and we review some algorithms. As you remember, in previous video, we started the concept of one variable unconstrained optimization, and I defined the method, the bisection method. In this video, as a new method, we start with Newton's method. The Newton's method in a general form in the most of the cases is more rapid in comparison with bisection methods. The basic idea behind Newton's method is to approximate fx within the neighborhood of the current trial solution by a quadratic function and then to maximize or minimize the approximate function exactly to obtain the new trial solution to start the next iteration. As you remember, guys, in bisection method, we only made our decisions and our intervals of the results based on the first derivation of our function. But here, in comparison with the other one, we use the second derivation of the function, okay, to find the optimal solution. So, as you see here, by letting xi plus 1 be the trial solution generated at iteration I, okay, it's more or less like our x prime that we had to start iteration I plus 1. So, x1 is the trial initial solution provided by the user to begin iteration 1. The truncated Taylor series for xi plus 1 is this type of relationship. But as we'll see in our next slide, we'll simplify it and we'll have one short and easy formula that we apply it in our Newton's method. But the only important item that you should see here is using of the first derivation, the function, and the second derivation of our function inside our formula. That is a big advantage in comparison with the bisection method. So, if we assume that our fxi, f prime xi and f second xi are constant, okay, we can simplify our relationship, okay, to this form, and on the right to 0 yields, okay, this relationship that we can easily change this relationship to this form, that our xi plus 1 is xi minus f prime, the first derivation of xi, and divided by second derivation of xi. As you see here, each x of the next iteration will be formed based on this form, okay? So obviously we need to have our starting point, okay, our starting x for our formula. So this is the key formula that is used at each iteration I to calculate the next trial solution xi plus 1, as I told you. Okay, after obtaining the trial solution xi to begin iteration I and then calculating the first and second derivatives at xi. So this is a continuous process that every time one xi will be used for xi plus 1. So this xi plus 1 is an xi for the next xi plus 1 and until the point that we find the optimal solution for our example. So, like the previous method, the bisection method, here we also need to define which one is our stopping rule. Iterations generating new trial solutions in this way would continue until these solutions have essentially converged, okay? But how? This essentially converged means our stopping rule. Which one will be our stopping rule? Our criterion for convergence is that the absolute difference between xi plus 1 and xi has become sufficiently small. How? Let's review. Another is that f prime x is sufficiently close to 0. Okay, is more or less like what we learned in our bisection method. So, if we define our epsilon as the value such that the algorithm is stopped when the difference, the absolute difference of xi plus 1 and xi should be less than or equal to our epsilon. So when we achieve this goal, we stop, and that x is our optimal solution for our problem. So to summarize the Newton's method, we should do some iterations. As an initialization, we need to select an epsilon, okay, and find an initial trial solution xi by inspection. Obviously, we set I equal to 1. So obviously I is equal to 1, I plus 1 equal to 2, and so on. The iteration I, we should calculate, as you remember the formula that we have here, the first derivation of our function and second derivation. The calculating based on xi of fx is optional. So, for each next steps, we need to set this formula that we proved in our previous slides. Xi plus 1 equal to xi minus first derivation of xi divided by second derivation of xi. So whatever we have here should put in our first and second derivation to form our xi plus 1. And as we learned before, the stopping rule is when the absolute difference of xi plus 1 and xi is less than or equal to the selected epsilon. So xi plus 1 is essentially the optional solution. Otherwise, reset to I equal to I plus 1 and perform another iteration. So it means that if this condition is not correct and is not valid, we need to add one more to our iterations and continue it up to finding the optimal solution. To clarify better the concept of Newton's method, let's review the example that we had in the bisection method by Newton's method. As you remember, this is our fx, 12x minus 3x4 minus 2x6. So, the formula for xi plus 1 will be having something like this. As you remember, this is our formula, and the first derivation is this one. The second derivation is this one. So in each derivation, we need to check our formula to find our xi plus 1, something like this. So obviously it is clear that these items are xi, as you see here. The first derivation based on xi, the second derivation based on xi. For example, if xi is 1, so it should be 1 plus 1 minus 1 elevated to 3 and the rest. So this combination gives me this xi plus 1. I need to check my stopping rule. Whenever it's valid, it gives me the optimal solution. Let's continue with the next slide. So after selecting epsilon equal to 0.00001 and choosing x1 equal to 1, we are able to start our table. In iteration 1, obviously when our xi is 1, and based on the formula that we have, we can calculate easily our f prime xi and f second of xi. If I put all of these items, this one, and this one, in my formula, my xi plus 1 will be this item. Okay? So, now we check our stopping rule. The absolute difference of 0.875 minus 1 is not less than or equal to this amount. So, this item we found it's not our optimal solution. Again, we need to start our next iteration. But what with difference? Now, this one is my xi. Okay? Again, I should put in the formula that we have, we obtain this one. The difference of this and this, the absolute form, is not less than or equal to this one. So, I should continue again and again, okay, up to this part, okay? Now, if I check the absolute difference of this xi plus 1 and this xi, it will be less than or equal to this amount, and it means that this 0.83762 is my optimal solution with a very high degree of precision. So this one was the summary of the solution of Newton's method. As you remember, as an advantage of Newton's method, in the starting of this video, I told you it's very, very faster in comparison with bisection method. As remember, if we wanted to do table 13.1 for bisection method with the same amount of epsilon, nearly 20 iterations would be required for bisection method. But as we saw in Newton's method, in 4 iterations, we could achieve our optimal solution that was 0.83762. The next part of unconstrained optimization is belongs to multi-variable unconstrained optimization. In the previous part of this video, we reviewed one variable unconstrained optimization that was an objective function in the form of maximizing a concave function fx with one variable. Here, the problem is maximizing a concave function of multiple variables that could be a range of the variables x that are x1, x2 to xn. So when there are no constraint on the feasibility values like the previous part, suppose again that the necessary and sufficient condition for optimality given by the system of equations obtained by setting the respective partial derivatives equal to zero. As you remember, the first derivation based on those variables is equal to zero. So, if in this system it's not possible to solve it analytically, so that a numerical search procedure must be used. So, in this type of nonlinear programming problems, we review the gradient search procedure that is an especially important one because it identifies and uses the direction of movement from the current trial solution that maximizes the rate at which fx is increased. This is one of the key ideas of nonlinear programming. So, in our next slide, we review this procedure of solving the gradient search procedure. As you remember in previous section, the value of the ordinary derivative was used by the bisection method to select one of just two possible directions, increase x or decrease x, okay? Based on the different steps that we had, we made this decision. So, in which to move from the current trial solution to the next one. So, based on the formulas and different steps, every time we had one new x prime that was less than or more than that the previous x prime. And there the goal was to reach a point eventually where this derivative is zero, okay, essentially zero. So obviously it was the point. Now there are innumerable possible directions. Why innumerable possible directions? Because instead of one variable, we have multi-variables, okay? So based on each of them, we can have one direction. So they correspond to the possible proportional rates at which the respective variables can be changed. So here in multivariable unconstrained optimization, the goal is to reach a point eventually where all the partial derivatives are essentially zero. Okay, so here is exactly the same, but instead of just derivation of fx based on x, here all the derivations, it means that derivation of fx based on x1, x2 to xn, all of them should be zero. Therefore, a natural approach is to use the values of the partial derivative to select a specific direction in which to move. Okay, so the explanation of this is exactly the procedure of gradients that we learn in our next slides. So, as we learned in the previous slide, in gradient search procedure, we identify and use the direction of movement from the current trial solution to which point with what objective to maximize the rate of increase of fx. Okay, so the gradient in a mathematical form, the gradient at a specific point, the point of x prime, is a vector that this sign is nabla, okay, of the first derivation of fx, that are all the derivation, the first derivation based on the variables of our objective function at point x equal to x prime. So once direction is identified, keep moving in the specific direction until fx stops increasing. In our next slides, we see how our fx stops. In this part of this chapter, we have two different search procedures, a gradient search procedure and Newton's method. Here we only review gradient search procedure. As a summary of gradient search procedure, we can see that, like the previous part when we had the problems of one variable on constraint optimization, we need to have an initial trial solution that we name it x prime and an amount of error, the epsilon, that we should check each time our problem with it. So to start, based on the initial solution, okay, and the first derivative of our initial solution, we need to form this equation in our objective function to see what happens. So based on our x prime, that is initial solution, we form our new x's, xj, the form of x prime j plus t, multiplied by the first derivative of our problem. In our example that it comes in next slides, we see it more clearly, this concept. So then if we find our f based on this amount, obviously we have a function based on the value of t. So based on the value of t, when we have this one, if we want to maximize this amount, it is enough to do the first derivative of that objective function and put it equal to 0 to find the t star that maximizes that amount. So based on the t that we calculate, we can reset our x prime with this formula. The current one plus t star that now is valid is exactly like this formula multiplied by the gradient that we calculated before. Then we need to check the stopping rule based on the epsilon that we selected. What is the stopping rule? The stopping rule is when all of the first derivatives based on our xj, when our j starts from 1 to n, should be less than or equal to the epsilon that we define, the error of tolerance. Let's continue. As an example, let's review one problem to clarify this concept. Suppose that we have this objective function maximizing fx equal to 2x1 x2 plus 2x2 minus x1 squared minus 2x2 squared. So the first one, for finding the gradient, we need to make the first derivative based on the number of variables we have in our function. How many variables do we have? Two variables, x1 and x2. So we do the first derivative based on our x1 and the first derivative based on x2. So we have these two new connections and these two new equations. So to begin the gradient search procedure, after choosing a suitably small value of epsilon, normally well under 0.1. So here we define our epsilon less than 0.1. Okay, so in our examples, in our exam, I will give you exactly what is this epsilon. And as you remember in the previous slide, we need to have one initial solution that here we define it as x equal to 0 and 0. Why 2? Because we have two variables. It means that our x1 and our x2 are 0 and 0. So if I substitute this amount in these two first derivative based on x1 and x2, the gradient of f0 and 0, our initial solution, is 0 and 2. So as you see here, because we defined our epsilon less than 0.1, okay, so at least we have one first derivative that is not less than 0.1, is not less than our epsilon. So the stopping rule says my 0 and 0 couldn't be the optimal solution for this example, and I need to reset this solution to a new solution to check if the next one is our optimal solution or no. As you remember, the next step to continue this search procedure is forming our xj's based on our current x prime. Okay, so if you remember, is our x prime plus t multiplied by the first derivative of that amount of x1 or x2. As you see here, we have 0 and 2t. So here we form our function of problem based on this new amount, this 0 and 2t. Okay, so if I put it in my problem, okay, as you remember, 2x1 x2 plus 2x2 minus x1 squared minus 2x2 squared, I just substitute 0 and 2t, it gives me 4t minus 8t squared. Again, what the procedure says, it says to maximize it, we need to derivate one time and equalize to 0. I derivate one time from this function based on t and equalize to 0. So if I put this one equal to 0, the t star, that is the t that maximizes this equation is 1 divided by 4. Now I need to reset my x prime. Okay, so it's exactly the same relationship, the initial one, the actual one, plus t star multiplied by the gradient. So my new point now will be 0 and 0.5. This is the new x prime. What is the next step? Check this one that is okay with the stopping rule. Let's see in the next slide. So from the previous slide, we found our new solution as 0 and 0.5. I need to substitute this one again in our first derivative based on the variables x1 and x2 to find them, the amount of them. As you see here, if I substitute these amounts in our first derivative, it gives me 1 and 0 as this amount. As you see, guys, here again is not optimal solution. Why? Because at least one first derivative is not less than or equal to our epsilon that we just defined, it less than 0.1. So we need to continue to the next x. So again, if I form our xj, the formula of xj, here I just wrote it in a complete form. The actual solution plus t multiplied by the gradient, this one plus t multiplied by this one, it gives me t and 1 divided by 2. So the objective function of my problem will be something like this. No, the objective function, if I substitute this amount in it, is f t and 1 divided by 2. I substitute t as new x1 and 1 divided by 2 as new x2. The final objective function will be something like this: t minus t squared plus 1 divided by 2. So again, here I need to find what t star maximizes this equation. To this end, I need to derivate one time from that and equalize that one to 0 to find t star. Let's see our next slide. So to continue the explanation of the previous slide, if I derivate one time from this t and 1 divided by 2 that gave me this one, my t star will be 1 divided by 2. If I substitute this one in the resetting x prime formula, 0 and 1 divided by 2 plus 1 divided by 2 multiplied by the gradient, the first derivative, the new point is 1 divided by 2 and 1 divided by 2. This completes the second iteration. With a typically small value of epsilon, the procedure now would continue on the several more iterations in a similar fashion. So here, with this point, I need to check if it's optimal solution for this problem. What should I do? I should put this point in my first derivative based on x1 and x2 to see if they are less than or equal to our epsilon that is under 0.1. The two iterations that we reviewed before are just summarized in this table. From a point 0 and 0, we just moved to a point 0 and 1 divided by 2. From this point, we move to this point, 0.5 and 0.5. But if we check this one, we'll see it's not an optimal solution. So we need to continue in different points, in different iterations to find the optimal solution. If we continue these many iterations, our final solution will be 1 and 1. If I check this 1 and 1 in my first derivatives, it gives me 0 and 0. As you see here, both first derivatives are less than or equal to our epsilon that is less than 0.1. So it means that this 1 and 1 is our optimal solution for this problem. This slide graphically shows the procedure, that gradient search procedure did during its steps. As you see here, from one side I have the variable of x2, from one side I have the variable of x1. So the initial point was 0 and 0. By the resetting and by the different iterations, different steps of this iteration, we found our next point is 0 and 1 divided by 2. Because this one wasn't our optimal solution, we reset and found our new solution, 1 divided by 2 and 1 divided by 2. This point as well is not our optimal solution based on the checking of stopping rule. And if I continue this table, I have these many different iterations that all of them will end in the point 1 and 1. As you saw, we discussed, because the first derivative of our example based on x1 and x2 for this point are equal to 0 and are less than our epsilon, so this point, this star shows, is the optimal solution. But Now, a question. If our objective instead of maximization was minimization, what should we do? It's very easy. Here, just to reset our x prime, instead of having plus t star multiplied by gradient fx prime, it now is minus, okay? And for sure, the only other change is that t star now would be the non-negative value of t that minimizes fx prime. Now it's less than or minus t gradient of fx prime. That is, as you see here, this amount is minimization. So again, we need to derivate one time and put equal to 0, the amount that minimize this objective function. So with this explanation, all the explanations of nonlinear programming and all of our parts of this subject are now finished. I hope these videos help you a lot to understand better what we learned during our classes. Thank you and have a nice time. Goodbye.